right, so we're looking at thermodynamics problem set, an FRQ from 1983 on the AP Chem exam. And in this reaction, we have 1 mole of carbon monoxide that reacts with 2 moles of hydrogen to yield 1 mole of liquid methanol. Notice the delta H of the reaction is negative 128.1 kJ, so we know that it's exothermic. That's important because heat is a product. That's important because increasing temperatures will decrease the yield of methanol. Decreasing temperatures would increase the yield of methanol. We're given delta H of formation data for carbon monoxide and also for methanol. Notice we are not given the delta H of formation for hydrogen gas or the delta G of formation of hydrogen gas, and that's because it's a standard element. There is no energetic cost or no free energy associated with an element in its standard state. So by definition, it has to be 0. So what I'd like to do is just do a modified table that includes diatomic hydrogen. So we have carbon monoxide, gaseous. We have methanol, liquid. And we have diatomic hydrogen, gaseous. And of course, we are interested in the delta H of formation and the delta G of formation and the standard molar entropy. Now, every molecule, every atom has a standard molar entropy. So we know that the values for delta H of formation and delta G of formation are 0, but we do not know what the standard entropy of formation is, and that's probably going to be required of us at some point in the problem. If we fill in the rest of our data, minus 110.5, minus 238.6. Notice the unit is a kJ per mole. That's standard in thermodynamics problems. And then we know that the delta G of formation of carbon monoxide is minus 137.3. And the standard entropy of formation. Now notice the unit is different because it's usually pretty small compared to delta G and delta H. It's joules per mole Kelvin. That's plus 197.9. So when we go to apply Gibbs free energy equation, in order for us to add or subtract delta H and delta S, we've got to convert this to kjoules, which means we'll just shift our decimal place, our decimal point 3 places to the left. And then finally we have negative 166.2 for methanol, and the S of formation is positive 126.8. Notice these entropy of formations are always going to be positive because there is an innate amount of energy dispersal that is associated with the presence of any kind of matter in nature. Delta H's of formation are always going to be negative because bond making is an exothermic process. The delta G's of formation should be negative, but sometimes they can be slightly positive. Now that we have all of our data, let's get to answering some questions about this particular FRQ. We want to calculate the delta G for the reaction. We're going to use Hess's law in order to do this. Delta G is equal to the G of formation of CH3OH minus, we need to look at the stoichiometry of our reaction. Notice there's 1 mole of methanol, there's 1 mole of carbon monoxide. There's also 2 moles of hydrogen gas, but 2 times 0 will be 0. So I'm simply going to leave this out of the computation. Plugging in some values now, I find that I'm going to have negative 166.2 minus a negative 137.3. Negative times a negative, of course, is a positive. And when I simplify the math, I'm going to get 28.9 kjoules per mole. Negative 28.9. Meaning this is a spontaneous reaction because it has a negative delta G. Okay, so for part B, we're asked to find the equilibrium constant. Need to remember the mathematical relationship that delta G, which we know is minus 28.9 kjoules per mole. And since I'm only producing 1 mole of product, I can just go ahead and simplify this, that it's minus 28.9 kjoules. This is equal to minus RT natural log of K. If we use just a little bit of exponential algebra, we find that K is equal to E to the minus delta G over RT. Now this minus sign is intrinsic to the formula. We already have a negative delta G. Negative delta G's will produce K values that are much greater than 1. So negative times a negative is a positive. However, the R constant that we're going to use is not the 0.0821 liter atmosphere per mole Kelvin, but rather 8.3145 joules per mole Kelvin. Because this is in joules and this is in kjoules, we're simply going to multiply this by 1,000. So when we go to set this equation up, K equals E to the 28,900 joules per mole divided by 8.3145 joules per mole Kelvin. In thermodynamic calculations, the temperature is almost always room temp. And if you are not given specific information about the temperature, you assume that is 298 Kelvin. This is really important because notice that all of my units cancel. I cannot raise an exponential if I have a unit. I cannot take a log if I have a unit. They must be dimensionless quantities. And so now I know I can simply plug this into my calculator. So if you're using a TI, just do second natural log, that'll be e to the x, and then you'll have 28900 divided by, open a parentheses, 8.3145 times 298, close a parentheses once and then twice. And we get a mathematical value of 1.0 times 10 to the fifth. This is important because if I have 1.16 times 10 to the fifth reactant molecules, so let's talk about carbon monoxide, that means one of them will not be converted to products, whereas the other 115,999 will. This is indicative of a very spontaneous reaction. And of course, if we go to check our mathematical answer, we find that it indeed is 1.16 times 10 to the fifth. Notice this is not a unit. It is a dimensionless quantity. It is a number. If the number is greater than 1, more than 50% of our reactants has been converted to products. If it's greater than 1, less than 50% of our reactants has been converted to products. So non-spontaneous doesn't mean you don't obtain product. It simply means you don't obtain 50% conversion. Part C is a very interesting question, and it looks like we're up against it at first glance. Calculate delta S for the reaction. I cannot invoke Hess's law the way that I could for delta H or delta G, because I don't know what the entropy of formation for hydrogen gas is. But here's what I can do. And this is where you have to think outside the box just a bit. If I find delta H, and I'm fortunate in this regard because delta H is actually given to me in the data, it is minus 128.1 kjoules per mole. We just computed delta G in part A. That was minus 28.9 kjoules per mole. I know that the temperature is 298 Kelvin. So I can use the first equation of free energy, delta G equals delta H minus T delta S, and solve for delta S. So delta S will be delta H minus delta G divided by temperature. Now we also need to notice something else about this reaction. If we look at the equation, we have 3 moles of gas producing 0 moles of gas. The entropy change must be negative, and so that allows us to check our answer. So now we simply have a bit of an algebra problem. We have minus 128.1 minus a minus 28.9 kjoule per mole, all divided by 298 Kelvin. Now this is going to be in kjoules per mole Kelvin. I would probably multiply this by the factor of 1,000 to get it in joules per mole Kelvin. So minus 128.1 minus 28.9 divided by 298 times 1,000 gives us minus 332.9 joule per mole Kelvin. you could certainly round that to minus 333 joules per mole Kelvin. And if we do that, if we check our solutions, we see it is precisely minus 333 joules per Kelvin. Since there's 1 mole of product, joules per mole Kelvin is still a valid unit that we can use. Now this sets up a problem that I warned we might see at the beginning, and that is once we know what this value is, we can now determine what the entropy of formation of H2 gas will be. Now we can apply Hess's law. Again, the reaction is CO gas plus 2H2 gas yields CH3OH. The delta S of the reaction, which we just found out, is minus 333 joules per Kelvin, is equal to the S of formation of CH3OH. We know that value, minus the S of formation of CO. We know that value. Of course, this is given information, minus 2 times the S of formation of H2. This is our unknown value. We have one equation and one unknown. We can solve this exactly. So all these units are the same. I'm simply going to drop them. I can find the S of formation of H2 as being equal to the S of formation of CH3OH. So let's go back to our data table. This is 126.8. Trying to get this so that we can there we go. We have 126.8 minus CO 197.9. Now I'm going to add 333 to the other side. 333, and all of this is going to be divided by 2. So now it's just a plug and chug problem. 126.8 minus 197.9 plus 333 divided by 2 gives us a value of 130.95, which we can round to 131 joule per Kelvin, equals the molar S of formation of hydrogen gas. And if we check our solution, let's do that real quick. 131 joule per mole Kelvin. Again, since we're making 1 mole of product, that's completely valid as a unit, as is joule per Kelvin. So now we've gone through one complete thermodynamic solution. And we're going to apply this logic in different ways on many different problems. This problem set contains, I believe, 24 different thermodynamics problems.